Okay, now this part here we will be dealing with bending stress in beams. We have done torsion, now this is bending stress in beams. Okay, so now for bending stress in beams, okay, you have to know this equation here, which we call the simple bending equation. Earlier we have the simple torsion equation, and now we have the simple bending equation. That is to measure the stress that is induced by the material of the beam when it is subjected to bending moment. So now M here, in these equations, the M, because I'm not going to look into the derivation of this formula, maybe in the later stage, but not now. So the derivation of these formulas will be temporarily put aside, okay, and then the theory in behind of this will be put aside as well, because here we will be mainly dealing with the main points and then start up with some work examples. Now M here is the maximum bending moment or moment at a section preferred, okay, which can be considered as constant. So now the first thing is you must know the definition of bending moment, that you should have done it in your static. So now for this section here, for this beam here that I've shown, this is a cantilever. With one end here is fixed, the other end is free. So you have this as called point load, the point load or the force. So if you take moment, and we can, from the diagram itself, we will be able to see, okay, or we will be able to say that the maximum bending should be appearing here at this point. So when you take this point here at which the moment that we need to calculate, we have to take now about this, okay, laser pointer here that is at this fixed end here. You have to take the force W multiplied by the perpendicular distance, that means the 90-degree length, starting from the reference point or the fixed point here to the point where the load is acting. So that gives you the length. So moment here will be force times perpendicular length. So that is W times L. And the unit for moment, okay, I remind you one more time, okay, which you should have already known long time ago. So W is the load or the force in Newton and length in meter. So unit must be in Newton meter, kilonewton meter, and so. Okay, so this is a cantilever. So for a simply, we call this a simply supported, where it's supported at both ends. Sometimes it is supported at points like this within the length. Any points, any 2 points will do. We call it as simply support. So we don't have to actually calculate the maximum bending moment here. We just use some certain standard formulas for all these 4 standard diagrams. So for this diagram here, the maximum bending moment actually appears at the center of the beam, because you can say it is symmetrical through the center here. If you draw an axis on this, you can see the mirror image on the other side. So we call this as symmetrical loading, and the maximum bending should be appearing at this point here, which is shown with my laser pointer. So the maximum bending moment is given as W, that is the load in Newton, times the length divided by 4. Okay, actually we can work this out, but then that is what you have done in static, so I'm not going to repeat this. Okay, so now this is a cantilever, but that it is not deal with point load. It is not dealing with point load, and it's dealing with what we call the uniformly distributed load. The uniformly distributed load, that is Newton per meter length. Okay, so usually in short form we call it as UDL. Okay, so the maximum bending moment will appear here on my laser pointer, and then the maximum bending moment formula is given as omega L to the power of 2 over 2, where omega is the uniformly distributed load, which is in Newton per meter. Okay, W is in Newton, omega is in Newton per meter. Okay, so this is a point load and this is UDL load. So that is the difference. So for cantilever, that is the maximum bending formula, moment formula. And for simply supported only with UDL, you have omega L squared over 8. But what happens if, let's say, for example, you have a beam with UDL load like that, and then with a point load acting at the center? If there is a point load acting at the center, so what you can do is you can use both these formula here, add it up by using the principle of superposition here, over here again. Okay, so that means if let's say you have a UDL load, a beam with UDL load with a point load acting the center, so the maximum bending moment should be WL over 4 plus omega L squared over 8. That is for the maximum bending moment, or the bending moment at any preferred section. Now, the next is I. I is the moment of inertia here. It's not the second moment of inertia that you have done for torsion. Torsion is second moment of inertia, which the second moment of area is taken to the z-axis. That means the third axis. Okay, so I is the moment of area. Second moment of area is not polar second moment of area. It's just second moment of area. And it is the second moment of area taken about the x and the y-axis. Okay, so now for example, now we have to know the standard formulas for all the moment of inertia, the second moment of area for at least rectangles and circulars. So basically, the I, or the moment of inertia, the second moment of area for rectangle, is given as BD cubed over 12. B is width, D is depth to the power of 3 over 12 for rectangular section, second moment of area. Okay, and then for circular section, it should be pi D4 over 64, where the D is the diameter. So when we look into that formula, the I, we need to know the I as well. So if we was to find the I, for example, if it is given as an I section, which you have already known, you must know how to find the moment of inertia of an I section beam like that. The cross section is I in section. So what you have to do is usually you have to split it up into 3 sections, 1, 2, and 3. Okay, so you must split it up into 3 sections. So then you must use second moment of area method to find out the moment of area of section 1 about neutral axis, because we are taking the moment about the neutral axis. That means we assume that the thing will bend, okay, across its neutral axis. And what is neutral axis? Neutral axis is which is a layer, a neutral layer or imaginary layer, which we assume that there's zero stress. That means if, let's say, for example, you have a beam supported or supporting a load, a point load like this W, we say, okay, the beam will bend, okay, will bend. Okay, what happens is the top layer will be subjected to compressive, the bottom layer will be subjected to tensile. So in between the compressive at the top layer and the tensile at the bottom layer, there's a layer which we call neutral layer, or the neutral axis, which is not compressive, nor neither it is tensile. So that is the neutral axis. So the I here is usually the second moment of area that is taken about the neutral axis. Remember what is neutral axis, okay? So where your stress is 0. So if this is a simply supported beam, okay, if it is a simply supported beam, then the maximum bending stress will occur on the topmost layer, okay, or at layers which is before the neutral axis. Now, how are we going to determine or find the location of the neutral axis? First thing is you must find out the center of gravity of the section that you refer. In this case, it is this whole I section that you have to know, okay, DCG, in order to locate your neutral axis. In order to find the CG of this, then you must first refer back to your first moment of area that you have learned in your static also as well. Moment of inertia also is in your static. So what happens is you have to again split into 3 sections and use a formula to calculate the CG of the section. But this is a symmetrical section, so automatically you can place the CG of this I section on the center of the cross section itself. So you can mark down your neutral axis. So if this is a simply supported beam like that, this is called simply supported beam. So when you have a force acting down like that, it causes the topmost layer is actually compressed, and the bottommost layer is actually stretched. So we say the topmost layer is compressed and the bottommost layer is stretched tensile, but on the neutral layer is 0. So that is your maximum and maximum bending stress, but it is compressive and tensile. But at the neutral axis, remember, on the neutral plane or on the neutral axis, the bending stress is minimum or is 0. That means always at the outermost layer of any section, if you refer to bending stress, when you refer to bending stress, at the outermost layer of any section that you are referring should be subjected to maximum bending stress. And as you move towards the middle or towards the CG or the center of gravity or neutral axis of the section, the bending stress will be 0. Now it is different between simply support and cantilever. So cantilever is just like, for example, refer back, this is a cantilever. So when you have this load acting on the free end of the beam, you have to imagine that this beam will be bent downwards like that. Look at my pointer. It will bend downwards like that. So you can say the top is stretched, the bottom layer is compressed. So that is why for cantilever, you have the top is tensile, the bottom is compressive, on the neutral layer is 0 bending stress again. Okay, now to locate the maximum bending stress, either is compressive or tensile, okay, or to locate the minimum bending stress, let's say I want to find bending stress up to this layer here, okay, then I must know the y value. The y value is always the vertical distance that you measure from the neutral axis to the section that you prefer. Let's say I want the bending stress, I want to measure the bending stress here. I want to measure the bending stress here. Look at my pointer. I want to measure the bending stress here. Then I must have this value of y starting from neutral plane to the plane which I wanted to find the bending stress. So this vertical distance is denoted as y. But as compared to this, okay, it is of course smaller until it reaches the neutral plane where y is 0. So you can say the bending stress is actually directly proportional. It's directly proportional to the y value, the vertical distance, y. Okay. So therefore, you can rewrite the whole thing or the whole equation into this form. So you can have sigma 1 over y1, for example, equals to sigma 2 over y2 equals to sigma 3 over y3, and so on. So you can form an equation like that. Okay? So that is your sigma over y. Now we know that E is Young's modulus. R is the radius of curvature. Just like, for example, if this is a simply supported beam. So if you have a load acting on this, it causes the beam to bend to form an arc, right? It will form as an arc. So from the end sections of the beam which has bent, and you draw a line forward and forward until both the line touches at one point. So that is where the center point is, and measure the length from the center point here to the deflected arc to the neutral axis. You get what we call the radius of curvature. and the Young's modulus. Usually Young's modulus, radius of curvature, moment and the second moment of area, they are all constants. So if m over I, E over R are constant, so sigma over y will be equals to constant. So that is why we say sigma is proportional to y. The y value, what is y value? Again, y value is the vertical distance that you measure from the neutral plane, from the neutral axis to the preferred layer, that you want to measure the bending stress. Okay, so let's say I want to find bending stress at the topmost layer here. Look at my pointer at the topmost layer here. So I must know the y is from the vertical distance, y is from the neutral plane, measure until here. So what is this y value? For example, here is 40 plus 10. So this y value should be 50. Then you can substitute your 50 into this formula with your m and with your I. You will be able to find out the bending stress at this section here. Okay, so that is the bending stress, and I have given you the standard formulas for circle, square or rectangle, triangle, and hemisphere. So these are the second moment of area for each cross section here, but most of the time we will be only using circle and rectangles. Okay, thank you for this section. Now, if you have any comments or you have anything that you want to ask, just put it on the comment section. Okay, comment section below on my YouTube channel. Okay, and then if you find that this is useful, please subscribe and like. Thank you very much. Bye bye.